I focused on escalator accident involving older passengers in Korea's national railway network. The main argument is simple. Why accidents happen and why they happen repeatedly? Maybe different questions. The presentation has three main parts. First, I will explain the background and research gaps. Then I will introduce the data and methodology. Finally, I will present the result and policy implications. Let me start with the question. Why does this research matter? Korea is aging very quickly. In 2025, more than 20% of the population was aged 65 or older, and this share is expected to reach almost 48% by 2070. So railway stations will serve more older passengers every year. At the same time, Korea Railroad Corporation's accident record shows that escalators account for about 30% of all in-station accidents, and nearly 70% of escalator incidents involve passengers aged 60 or above. This means escalator safety is not just a maintenance issue. It is also about whether older passengers can use railway stations safely, comfortably, and independently. Previous studies have helped us understand the main factors behind escalator accidents. However, they have two important limitations. First, most studies are based on single city or transit systems such as Guangzhou, Beijing, New York, Seoul, and Daegu Metro. This makes it difficult to generalize the findings to a nationwide railway network. Second, some studies rely on accident reports submitted to regulatory agencies. These reports tend to focus on more serious cases, so minor incidents may be missing. But for older passengers, even minor accidents can be important, especially when they happen repeatedly. So the two main gaps in the literature are limited geographic scope and incomplete accident records. There is also a methodological gap. Previous studies have used methods such as chi-square test, a hidden matrix, and negative binomial regression. These methods are useful, but they do not fully address one important feature of the accident data. When we look at accidents count for each escalator, many observations have zero accidents. Standard count models do not clearly separate these zero cases from positive accident counts. These three gaps define the objectives of this study. First, this study expands the scope by using nationwide panel data from Korea's railway network. Second, it uses operator-maintained accident record, which include minor incidents that may be missing from regulatory reports. Third, it applies a hurdle Poisson model to separate accident occurrence from accident frequency. This distinction is important because first-time accident and repeated accident may require different safety strategies. Therefore, the main contribution of this study is linking risk factors to stage-specific safety policies. Let me briefly explain the data. I combined three KORAIL datasets: escalator facility data, station information, and accident records. The accident records were reported by station staff, including cases reported by passengers or found on site. The final data set covered 306 stations, 2,875 escalators, and 14,349 escalator year observations. The original accident data included 3,529 records involving passengers aged 60 or older, after excluding 941 records that could not be linked to a specific escalator. The final accident sample included 2,588 cases. The unit of analysis is the escalator year. The variables are divided into two groups. The first group includes escalator characteristics such as length, height, speed, installation and age, angle, and direction. The second group includes station level factors such as station type and region. Station types are classified into ground level, underground, overtrack, and underpass stations. The diagram below illustrates the structure of each station type. Looking at the descriptive statistics, annual accident counts increased from 581 in 2020 to 835 in 2022 and then decreased slightly after that. This may reflect the recovery of railway use after the pandemic. the accident count variables is very sparse, the mean is only 0.18 accounts for escalator year, while the maximum is 15. By station type, overtrack stations have the highest number of accidents. By region, accidents are concentrated in the Seoul metropolitan area. But these are low counts, not adjusted accident rates. They do not account for differences in the number of escalators or passenger volume across the station and region. So in the regression model, I include regional controls to partially account for these differences. The direction variable shows an important pattern. Upward escalators make up 55% of observations, but they account for 72.4% of accidents. This means upward escalators appear more often in accident record than their share in data. This pattern is also consistent over time. In every year from 2020 to 2024, upward accidents are more than twice as high as downward accidents. One possible reason is that boarding on upward escalator requires more precise timing, length, strength, and balance control. So we will see later, upward direction also become one of the strongest predictors in the model. This slide shows accident patterns by escalator characteristics. On average, escalators are about 70 meters long, 8 meters high, and operate at about 25.2 meters per minute. The average installation age is about 11 years. Our table summarizes the mean, standard deviation, minimum, and maximum value of main variables. Most escalators have a standard 3-degree angle, so there is limited variation in the angle variable. Again, this graph shows low accident counts, not risk rate. A higher bar does not necessarily mean that the escalators in that group are more dangerous. It may simply mean that more escalators belong to that group. So these descriptive statistics help us understand the overall pattern, but the regression model is needed to estimate the effect of each factor more clearly. Let me explain why I use the Hurdle Poisson model. In the dataset, there are 14,349 escalator year observations. Among them, about 21.5% have zero accident. But zero accident do not always mean that escalator is safe. It may simply mean that fewer people used it or that no accident happened by chance during that year. So I separate the accident process into two stages. Stage 1 asks, did any accident happen? This is method with a binary logit model. And stage 2 asks, if at least one accident happened, how many accidents occurred? This is modeled with a zero-truncated Poisson model. This two stages structure is useful for policy. Stage 1 is about prevention or stopping first-time accident. Stage 2 is about mitigation or reducing repeated accident. I compared three models, standard Poisson, negative binomial hurdle, and hurdle Poisson. The standard Poisson model was not appropriate because it does not distinguish zero accident cases from positive counts. The negative binomial model has also tested, but dispersion parameter was not significant. So I selected hurdle Poisson model. The fit statistics shows that adding explanatory variables improves the model compared with the null model. Rather than focusing on each number, the key point is that the final model explains accident patterns better. The variables are allocated by this mechanism. Station type, region, and age and angle are used for the occurrence stages, while length, height, and speed are used for the frequency stage. Direction is included in both stages because it affects both boarding and lighting stability. So stage 1 shows which factors affect accident occurrence. The strongest factor is upward direction. The coefficient is 0.646 and it is highly significant. This means upward escalators are more likely to have at least one accident than downward escalators. For older passengers, boarding on upward escalator may require more precise timing, leg strength, and better balance. Station type also matters. Overtrack stations shows higher occurrence risk, while underground station shows lower risk. This may be because overtrack stations are more exposed to weather and environmental changes, while underground stations have more controlled environments. Region also shows differences, with 전라남도 showing a positive coefficient. This may reflect differences in ridership, station context, or elderly population share. Moving to stage 2, this part explains accident frequency. Escalator length has a positive effect, meaning that longer escalators are linked to more repeated accidents. This may be because passengers need to keep their balance for a longer time. And height and operating speed shows negative effect, which may look unexpected. Taller escalators may be easier to notice, so passengers may behave more carefully. For speed, the result does not mean that faster escalators are safer. Rather, the key point is to keep the speed steadily and moderate, and passengers can predict the movement. Upward direction is also positive in stage 2. This means upward escalators increase both the chance of accident and the number of accidents after one has occurred. This slide summarizes the core findings of the research. The main point is that accident occurrence and accident frequency is driven by different mechanisms. In stage 1, which asks whether any accident occurs, the important factors are direction, installation age, installation angle, and station type. There are mainly baseline conditions that affect a chance of the first accident. Stage 2, which asks how many accidents occurs after at least one accident. The important factors are direction, length, height, and speed. This means repeated accidents are more related to exposure during the ride and escalator operating condition. The one factor that appears in both stages is upward direction. Its coefficient is positive in both the occurrence model and frequency model. So upward escalators are not only more likely to have an accident, but also more likely to have repeated accidents. This supports the two-stage model approach. So the take-home away is occurrence and frequencies are different processes, but upward direction is consistent risk factor across the board. The findings lead to 4 policy directions. First, exposure management. Longer escalators are linked to more repeated accidents, so the issue is not simply station depths, but continuous exposure time. Intermediate landing, rest area, or alternative route can help reduce long exposure where feasible. Second, speed management. The results do not show that slower is always safer. KORAIL speeds are already conservative, so further speed reduction may not improve safety. The goal should be consistent and moderate speed, so boarding and alighting remain predictable. Third, station type prioritization. Overtrack and underpass station shows higher occurrence risk, likely because they are more exposed to weather and circulation complexity. These station types should be prioritized for safety audit and maintenance. Underground stations suggest that controlled environments can provide safety benefits. First, direction-specific interventions. Upward escalators are important in both stages, so they need targeted improvements. Clear boarding zone markings, step edge highlight, and station zone queue and handrail guideline can improve boarding clarity. Let me now discuss the limitation and future research direction. First, there is a methodological limitation. The hurdle model assumes that the occurrences stage and frequency stage are independent. However, there may still be hidden differences across the escalators that are not fully captured in the model. So in the future research, random effect or parameter hurdle model could be used to better capture this escalator level. Also, adding station year ridership data would also the model to estimate accident rates rather than only accident counts. Second, there is a data scope limitation. The current dataset does not include pedestrian volume, weather, and time of day variables. Also, because some accident records are manually entered, they may be reporting omissions. Future research should integrate richer operational data and improve accident report form and data management protocols. Third, there is a limitation in generalizability. The findings are based on KORAIL-operated railway stations, therefore they should not be applied uniformly to all railway or metro system without further validation. Future studies should test the findings across different station type, operating contexts, and transit system through field survey, behavior observation, and intervention trials. The following slides provide the references that support this study. This concludes my presentation. Thank you for your attention.